Okay.
Now we're recording.
Yep,
Okay.
we're recording.
So I'm kind of going to develop some concepts on these slides, the next few slides. So bear with me. This is kind of a weird idea. So mutual inductance. If you've got two coils, so this picture shows two coils cut in half, so we're seeing the cross section, but you have to imagine they're full coils, right? And they're near each other. Then the changing current in one of the coils will produce a changing magnetic flux in the other coil. So coil 1 has current 1 in it. If that current is changing, the B field that it creates is going to change through this coil. That's going to induce an EMF and an induced current in the second coil. So as that B field changes through the second coil, that changes the flux through the second coil, right? Flux is the number of B field lines going through it. So just for example, let's say the current 1 is increasing, then you're going to have an increase in B field lines going through the second coil. So you'll have an increase in flux through the second coil. So that induced flux, that increasing flux in the second coil induces a current I2 and an induced EMF 2 in the other coil. So if I1 was increasing, then what's the direction of the current in the second coil, the induced current in the second coil? This one says up for the section we see. What's the direction of the current in the other coil?
Down.
Down.
Be going opposite?
Yeah, it's going to be opposite because it wants to create a B field that's
That's
opposite.
opposite.
So the induced EMF in the other coil will then, because it creates its own B field, right? Its B field is opposite. So that induced current and induced EMF from this coil will then induce a new current or a new EMF in the first coil. So the first
Opposite.
coil created an induced current. This
Opposite.
induced current creates another induced EMF in the first coil.
To make it go opposite?
Well, let's see, if this is increasing, then this would be opposite current increasing in the opposite direction. So that would boost this current more. So it would be inducing a current in the opposite direction, so that's adding to the current that was already there. So it's kind of this weird
So wait a
idea.
minute, so if it's going this way on this coil,
Which coil? 1 or 2?
the one,
Okay.
and then it gets to this coil, which it's not going this way, now it's going this way.
Then that one is going to
It's gonna
induce
go
a
right
current
here,
in the same same direction that this one was already going. It's going to boost the current.
because it's the opposite. Okay, got
Yeah.
it. So it's opposite, yeah, got it.
So the induced current in the second coil is called mutual inductance. And then the fact that the second coil induces a current back in the original coil is self-inductance because the first coil started it. So he kind of started the process and that induced a current in himself. Self-inductance, okay?
Goodness gracious.
So any questions before we move on? Because it gets weirder. So
Great.
I want to make sure you understand this before we get weirder.
And the direction of the current of the self-induced current is this in the same direction, and it adds to
The original
The original,
current.
okay.
Yeah. Ready
okay.
for weirder?
Sure.
Great Scott, Marty.
If you remove the second coil, it's not actually necessary to generate an induced current in the first coil.
After you started it?
Wait, say that again?
What?
That didn't.
It's weirder, right?
But no.
So we still get self-inductance in the first coil, even if there isn't a second coil that had an induced current.
Okay.
So that magnetic field's still there, even though it's not coming back from another inductor, there's still some magnetic field there that's kind of flowing back into itself.
Wait a minute. That doesn't make any sense. What do you mean you don't need a second coil?
I told you it was weird. It's weird mostly
So where's
because
that coming from?
I don't have a really good explanation, but it happens.
I'm a doctored off physicist, damn it.
So if you'll notice, if if you'll notice that most of our conversation with mutual inductance was talking about the induced EMF. And so we were mostly explaining it with currents, because currents make a lot of sense. Induced EMFs are a little bit harder to grasp in a loop. So the induced EMF is a voltage, basically. And so we learned last week that if you have an induced current, you do have an induced EMF. So you get some sort of voltage. And so you could think of that voltage as sort of like a store of energy, or sort of like a battery, where it's storing energy that can be used later. And so the second coil gets an induced EMF, and then that causes the first coil to get an induced EMF. And then the weird part is that if you remove the second coil, you still get an induced EMF in the first coil. So just the fact that it's a coil with current running through it, a changing current running through it, will create this self-induced EMF. Okay, and so it's sort of like a store of energy. If the current's changing, then your coil has a store of energy that you can use for something else. Okay. Any questions on that? I don't know if I'll be able to answer them because it's weird, but I'll try. Did you have one, Lane?
So,
Jacob?
Well, and yeah, so in circuits classes, they taught us that inductors store energy.
Uh-huh.
And is that how, and we don't actually know?
Well, there's probably somebody who's got a better explanation than me.
Right, I mean, right now.
I don't really understand it, so I can't explain it
I was
to
really
you,
hoping
but
for that answer.
I'm not saying this is one of those mysteries of physics. I'm just saying that I don't understand it well enough to give you
Okay.
more information. But the book, as you know, is very verbose. Their explanation might be more detailed and maybe makes more sense, you know, because I'm kind of just saying this is what happens. I'm not really sure why.
so it's
It doesn't make a lot of sense to me how it happens without that second coil there, but the book might have a more robust explanation.
so is it the same phenomena with or without the second coil, or is it a little different? I mean, is it stronger or weaker?
Apparently, and again, asterisk, because I'm not solid on it, but apparently it's the same if with or without that second coil. Because the second coil wasn't connected to anything. It was just sitting there. And the fact that it has a changing B field running through it means it's going to get a current running through it. So it's just an unconnected coil. And it kind of makes sense that just a piece of metal near another coil doesn't necessarily need to be there for the coil that's actually connected to a battery to show the same effect. And so you get that effect whether the second coil is there or not.
I guess it was just the idea of this dynamic happening between two coils, that sort of makes sense, but
Yeah.
then, because it's acting on the first one, but then what's acting on the first one in absence of that second coil? That doesn't make sense.
Yeah, I agree.
Okay. Yeah,
I would say that, you know, if it's troubling you,
read the book.
then try reading the book and hopefully the book is
Yeah, helps.
hit and miss sometimes when the book
Yeah.
does a good job of explaining something. I have read the book, so maybe that's proof that it's not so good at explaining things, because my understanding came from the book. So and when you guys take
Fair enough.
circuits, do you get into the nitty gritty? You just learn that this happens. You don't
Right, how it
learn
affects
why.
the circuit.
Yeah, okay. Well, I need to do a better job than as your physics instructor to explain it, because that's why you're here. You learn the whys here, you learn the hows in circuits, so. So maybe I need to find a better resource than our physics textbook to explain this, but it's just a weird idea. I think there's a lot of phenomena in physics that are kind of just weird.
Physics world?
Yeah.
So the big takeaway is that it does that.
It does that, yeah, and we're going to use that. In fact, a lot of this lecture is kind of just like circuits. It's like, this is some neat equations, now just plug it into a circuit and see what happens. So most of the lecture is going to be actually plugging these into circuits.
So self-induced EMF only happens with a changing current.
Absolutely, yeah.
Whereas if you have two inductors, you don't have to have a changing current to have the induced EMF?
No, there would have to be a changing current.
Okay.
Yeah. Yeah, so if you just have two coils with current running through one and not through the other, it's not going to do anything to that second coil.
When it's
So,
constant, then-
so I guess the take-home message is we get this self-induced EMF. We didn't get into this much last week with the direction of the EMF, but this week we're going to talk more about the direction of the EMF, and that's based on whether the current is increasing or decreasing. Okay, so inductor EMF, which is, as it says in parentheses, that is the induced EMF, or self-induced EMF. Okay, so we use this loopy E. Again, so that's just the EMF we've used before, but it's related to the inductor, so it's sub L. Units are volts still. And our definition is minus L di dt. So right there in the definition of inductor EMF, you've got a change in current. So if this is not changing, your induced EMF would be 0. And then it's also related to the size, the value of the inductor. The minus sign, again, this is like one of those minus signs that's a reminder more than a rule that necessarily always has to be followed. So the minus sign just tells you that the EMF opposes a change in the current. So that's very similar to what we talked about last week with these induced currents. It opposes a change in current, and we'll talk about what that means direction-wise in a minute.
So me?
The sign up. Signing.
All right. So your inductor is put in a circuit to create a B field. That B field can be used for a variety of purposes. One application that I'm thinking of off the top of my head is there were these EV cars, electric cars that came out in the late 90s. Anybody here seen Who Killed the Electric Car? It's a cool
I've heard of it, I
documentary.
haven't
So
seen it.
they talk about a variety of EV cars that came out right around the late 90s at the same time. They all use this same charging paddle, and a lot of charging stations went up in California and other places that was specific to this charging paddle. And I had my electric vehicles class in grad school was taught by the guy that invented the paddle, so it was cool. So the paddle was, it was this sort of plastic, it looked like a paddle, right? And it had some width to it. And inside there was a coil of wire. And that would just plug into this plastic hole on the front of your EV car. So you could put your hand in there, it's plastic, you're never gonna come in contact with the battery voltage, you know? So very safe. You know, your little kid could walk up and stick their hand into the port and nothing would happen to their hand. But you put that paddle in there, inside that hole, right, there's a coil on the other side. And so your charging paddle has current from the wall outlet, drives current around the loop, that induces a B field, which induces a current inside the car loop, which charges the car.
Oh, okay.
It's actually pretty inefficient, which is why they abandoned the paddle when they got the new charging stations with new plugs now. And it's like a high voltage port. It's like the 240 volts instead of the 120 you have in your house. But the paddle works well and it's very safe, but it took a long time to charge. Yeah.
Isn't that similar to like when you set something in and it's not contacting it, like your phone or whatever, that's good chargers?
Yeah. So there's some you can make these actually. That would be a cool senior project for somebody. But you can create a flat surface with a loop of wire in there, and if you put your phone on top of the flat surface, it's creating a B field, and that will charge your phone if you've got the correct circuitry in your phone to.
If you don't fry your phone.
Yeah, if you don't blow it up.
Yeah, I mean you gotta
Do some
get a
equational
refurbed cheapo phone to work on.
test it.
But
Magnetic field never hurt electronics.
oh man, this I just saw, and I didn't read the article, but I just saw this last night. That they said that magnetic fields, and showed this like crazy picture that looked like a black hole. It said there are magnetic fields in the universe that are stronger than black holes. And I was like,
Oh, I saw
okay, so- wow.
the title
Yeah.
of that.
Yeah.
Yeah, but I didn't get a
Stuff
chance
could
to read
get
it.
out.
It does make a lot of sense because I just gave this lecture to my 223 folks where we were comparing the forces, and the gravitational force we already talked at the beginning of this term. It's really, really, really small compared to electricity and magnetism forces. So it makes sense that, you know, every particle, every electron creates a little magnetic field if it's moving. So somewhere in the universe you could have these really, really strong magnetic fields that would be stronger than gravity.
Hmm.
Kind of scary to think about. I mean,
In that case, it would
we
just act like
calculated,
gravity, though.
what's that?
I was gonna say, in that case, then they would pretty much act like gravity.
In a lot of ways, because we said electricity and magnetism both dropped off like 1/r². We calculated, so I know this is off topic, but we calculated that the electric force was Q1, Q2 over r².
Wow, okay.
So this drops off like 1/r². The gravitational force we got at the beginning of the term was Gm1, M2 over r². They both drop off like 1/r². So the field, our 1/r² equation is that inverse square pattern.
Oh.
So the field is really, really strong when you're nearby, and it drops off pretty quickly the further you get away. But that's the same for gravity and electric force. We just know that gravity was 10 to the negative 30 times weaker.
Wow.
You know, so a magnetic force works very similar to electric force. So it's going to drop off like 1/r² as well. But it's 10 to the 30 times more
Bigger.
strong than gravity. So anyway,
So
since we've been
it sounds
talking
like
about
that can
magnetism.
pull electrons out of black holes,
Maybe.
which.
Could a black hole get like kind of a charge going?
But nothing can escape.
I don't know.
Yeah.
I don't
Because they
know.
were talking about how things can get out, and if a black hole got charged, that would make things get pushed out, wouldn't it?
I don't know, maybe that's the explanation, because they show, when we looked at our black hole picture, we saw that the gamma ray bursts that we
Oh,
detect
right.
are these top and bottom ends of the black hole that are ejecting stuff. And so maybe that's the mechanism, is it's creating inside that black hole, which we
Like
can't
once things
see,
get all smushed together, then it could get like
like a magnet.
polarized or something.
Yeah, like
Push things out that.
that could very well be. I mean, that may be the explanation for why stuff gets ejected from a black hole. If it's the force, the repelling force is that much stronger than the gravitational force trying to pull it back in.
Yeah.
Anyway, I know it's like not really on topic, but in the news.
Similar.
What's Steve talking? 222, we just solved the mystery of black holes.
Make a note. Make a note. We did it in here.
Take that, Stephen.
Okay, so going back to inductors, you guys have taken circuits. So does anybody have another example? I gave the example of the charging paddle. Transformers, I believe, make use of induction.
Yes.
Anything else that I'm unaware of? You probably know more about
Correcting power factor.
correcting power factor. Okay, sort of self-correcting for a system.
Yeah.
Okay, that makes sense.
Well, there's all those like battery things, like your toothbrush or whatever, that you don't directly plug in.
Oh, right. Okay, the ones that charge the port. Similar thing, the port is under it, but it's not.
Yes.
There's no plug.
You set it on a base, but it doesn't plug. It just
Yeah, yeah.
rests in a thing.
I had a student last term that worked for like an air conditioner company, said something like the safety switches or something with the air conditioning units use inductors. I don't know how that works, but there you go. So there's a lot of applications, and I'm sure you'll do a lot more application stuff in circuits. We're going to talk about RL circuits in detail, and we're going to briefly talk about LC circuits and RLC circuits today. But you'll get the benefit of building those in circuit class, and we're not going to do that this term. So let's talk about the direction of that induced EMF. Since we know it's going to oppose a change in current, then we can figure out the direction. So if the current through your inductor has just been turned on, then the current will start increasing as it goes through the coils of your inductor. So here you've got I increasing coming into your inductor. So our right-hand rule says if that current is increasing like this, then you can do your right-hand rules and figure it out. The net effect is that you're going to get an induced EMF that's opposite to that current. So your induced EMF will point upward. And at the moment that the current starts, that induced EMF is going to be so strong that it blocks that current completely. So at time equals 0, no current will actually flow through your inductor. And then gradually over time, as the current levels off, because it starts out and it turns on and it starts changing very quickly. But as the current changes slower and slower, then the induced EMF is going to reduce its effect until you get to a point that the current is steady, and so your induced EMF goes away once the current is constant. And then the moment you turn off your current, so you unplug your current from the switch. or you
After
open
a
the
period of
switch.
time or
Yeah,
something.
yeah.
Okay.
So you went from current being constant, and now suddenly your current's dropping off, like that. You're going to get an induced EMF that's in the same direction of the current because it says, don't go away. It's, it opposes any change. So it's in the same direction of the current, and it'll keep the current at the level it was at before for a while. But again, eventually the resistance in the wire itself is going to deplete that current. So the current will eventually dissipate, and as it dissipates, your induced EMF will go away as
So
well.
like those flashlights, right? That you wind up to, or,
Actually,
you know what I'm saying?
I know the wind-up ones. Probably, but have you seen those shake flashlights?
Yes.
That's the same
That's the
concept.
okay. That's what I was thinking.
The shake flashlights. Not going to do the motion.
Good idea. Smart. Especially when you don't have the
Thank you.
flashlight.
That's right. Yeah.
Post
Don't
that
call
on
it video.
YouTube. Yeah. The blooper reel. Be famous.
With the audio cut out, but.
Yeah, that would be great.
Physics teacher gone wild.
Oh boy.
Yeah.
You dub over audios and remix to something else I said out of context. Did I say last week it's not the size of the field? Yeah.
Some, but I can't recall.
A weekend project now.
Okay, so using what we know now, we can try example 30.4. This says, if the current in the toroidal solenoid we solved for in this equation increases uniformly from 0 to 6 amps in 3 microseconds, find the magnitude and direction of the self-induced EMF.
This is 3.4, right?
Yeah, 30.4. Okay. So we solved for L, mu naught n squared A over 2 pi r. I'll just do this work over here. .4. So from example 30.3, L is mu naught n squared A over 2 pi r. And so now we're trying to find the magnitude and direction of self-induced EMF. So find E sub L. And we're given that the current changes, the change in current is from 0 to 6 amps, and the time is 3 microseconds. 3 times 10 to the what?
6.
Negative 6 seconds. Okay, so as long as it's changing uniformly as a function of time, then we can replace our di dt with delta I dt. And we don't really need the negative because that's again, the minus sign is a reminder that it opposes the direction. We're going to use logic to figure out the direction of the induced EMF.
Logic should be delta I over delta T.
Delta I, yeah, thank you.
Logic.
So, plugging in our L equation, mu naught n squared A over 2 pi R, and then delta I over delta T. Example 30.3 didn't have numbers. I'm guessing that they mean the numbers that they found in their evaluate section. Okay. So in the evaluate section, they found that the inductance was 40 times 10 to the minus 6 henries. So we can do 40 times 10 to the minus 6 henries here. And then what do we put in for delta I? 6, yeah.
Negative
Six.
6A? No.
Yeah, we do final minus initial.
So,
Actually, I probably shouldn't write 0 to 6. I should write
6.
I final minus I initial equals 6 amps minus 0 amps.
Okay,
That
6
makes
amps,
sense.
okay,
Yeah.
good.
Okay, 6 amps, and then the time was 3 times 10 to the minus 6 seconds. Okay. You could probably do this in your head, because the 10 to the 6 here will cancel the 10 to the 6 there, and then you just have 40 times 6 over 3.
No.
You get a nice even number. Anybody?
8.
80? 80. Okay, so that's the value of the induced EMF. Anybody have a, I guess we would need to know what the direction of the current was going in the first place. Picture.
So I presume.
Okay, so if the current is decreasing, is it, no, it's increasing, I increasing. So if I is increasing, based on this picture, we see that if I is increasing, your induced EMF would be upwards. And so from the picture, it just shows it's opposite to the direction of the current. So from that, we can guess then what would the direction of the EMF then be? I don't know how.
Wait a second.
I mean, this is generally kind of going this way, so would that mean that the induced EMF would
The
be?
opposing.
Yeah, going the other way.
Going to the left. Yeah.
Let's see what they say for the direction. The current is increasing, so according to Lenz's law, the direction of the EMF is opposite to that of the current. Okay. Is that? The EMF is in the direction from B to A, so that, I have to look at their picture to know where B and A is. I don't see B and A. I don't know what figure they're referencing. Figure 30.6C. Well, you get the gist. It's opposite to the direction of the current. So the current is generally to the clockwise,
Yeah.
then the EMF would be in the counterclockwise direction.
Makes sense.
So we just say like opposite of current?
Yeah, that would probably work better for a toroid.
So, I mean, the EMF is induced in the wire, so is it gonna be?
Along that,
Is
I
it
don't-
along, it's not in the toroid, right? It's actually in the wire that we're talking about?
So it's not
I need a
magnetic.
picture
Because it would just be the opposite in the wire.
in the wire.
Yeah.
But when we do this picture, the wire is coiled and the EMF is running through the length of it like that.
Right, yeah.
And I'm not sure why I haven't talked about this. Maybe this comes later. But we can't actually measure the EMF inside the solenoid. So we're just measuring it across the solenoid.
Right.
So probably because the EMF is doing something like this inside the coils themselves. So when it's a toroid, I'm not sure how you would actually measure that unless you pulled the wire out like this and had these leads, and if the current was,
Right, and that's kind of, the picture kind of shows two wires popping in and out of the toroid, which is probably,
is that, okay. Because that's where you would actually be able to measure the EMF is, once you've got those terminals. So chapter 30, picture 6. That's the one they're telling us to reference. They don't have a toroid. Those are solenoids. That's not helpful. Yeah, so I think maybe more useful is if you're driving current through this way, then your induced EMF would be like that. So this port would be 0 volts, and this would be your high voltage, say 80 volts that we measured. So any other questions about example 30.4?
So basically, it's not continuous, it's the two coming out, is how we
Analyzed?
Yes, whatever it's saying.
Analyzed it? Yeah, so, yeah, I think
Okay,
in practice, you wouldn't measure it in the toroid, you'd measure it from 2 leads coming off the toroid.
similar to those pictures.
Yeah, exactly.
I would think that if you measured it in the toroid, it would not show you any EMF difference because you'd be
Continual.
basically measuring it from one part of like,
One little section,
Yeah,
so
of
you wouldn't
wire.
get the full 80 volts anyway. Is that what you mean?
I mean, yes, that and because of the way it's wound, like all that, those properties are like induces the EMF difference. So if you just measure across a wire, it's not the actual effect of the whole thing.
Oh,
You're just
right,
actually
because
measuring a wire.
the wire would be straight,
Right.
sort of close to straight at that point.
Right.
Yeah, okay, I believe you. Good explanation. No, I agree, I think that's probably where that comes into play when they say we don't ever measure in the coil itself, we just measure across it, because you don't actually see the effect if you were trying to measure in the coils
And you would
themselves.
just get zero.
Yeah. Okay. Next slides. Okay, so energy, we kind of already described the induced EMF as energy that can be stored by your inductor. So, we talked about energy storage in capacitor plates before, so going back to this concept, you got 2 oppositely charged particles or conductive plates like a conductor. You can set up some sort of potential difference in between those plates, and in essence you're creating a stored energy that you can use later. So that stored energy was electrical potential energy, and then you can recover that when you discharge the plates, if you allow the plates to move together or whatever. So that was that ideal situation where you assume no loss in a capacitor, you could store energy indefinitely. So for magnetic fields, you can also do that with the inductor. You can store magnetic potential energy. And our equation here is 1/2 Li squared. So this is stored magnetic potential energy. And what are the units that we know and love for energy?
Joules.
Joules. Yep.
No one will. Jewel. Sure.
I know Jules.
Bright and shiny things.
You know Jules. I had Jules in my class last year. So there you go. If they ask you for energy stored in an inductor, that would be what you want to use. Okay, now we're going to get into how RL circuits work. They're very similar to how RC circuits work, so I'm just going to throw up here our equations we had for charging and discharging of an RC circuit. What is the general form that pops out in all of these equations?
E to the negative T over RC.
Yeah, so you've got some kind of exponential, and that
Is that
exponential term.
decaying, going away, right?
What's that?
It's like decaying, going away.
Sometimes, so sometimes it was decaying.
Okay.
If it's just e to the stuff, and in the case where we got 1 minus e to the stuff, that was the times when it was increasing. Yeah. Yeah. So that general form of the equation, that's going to come back for RL circuits as well. Okay. So this is what do they call this? Series RL circuit we're going to analyze. So we're not going to talk about other types of RL circuits. So we're just talking about the series RL circuit. And that's series because the resistor and the inductor are in series with each other. And then we've got this funky switch here, positions A and B, and then your switch can move between positions A and B. And then you've got some kind of battery voltage. So instead of charging and discharging, that's how we talked about the RC circuit, now we've got rising current and falling current. Those are the two states that you can have. And that how our EMF is going to, or our induced EMF is going to behave is just how we said before. As the current is rising, then your induced EMF is going to oppose it, and as your current is falling, your EMF is going to add to it. So we move the switch to position A, and that allows current to flow. So at that time equals 0, current is rising across your inductor, and your inductor then is going to, your induced EMF is going to oppose it. So this single loop we can do a loop rule equation on. This is how it looks, just like the RC circuit, it's a differential equation. I'm not going to ask you to solve it, this is the solution. Okay, so our solution for the current as it changes with time through the inductor is the battery voltage, not the, so this is E, that's the battery voltage, not the induced EMF, over the resistance, and then 1 minus e to the minus RT over L. And then the next one I replaced R over L with 1 over tau sub L. So that 1 over tau sub L is called the inductive time constant, and it equals L over R. That's different. So R, for the RC circuit, the capacitive time constant was RC, yeah. And so for RL circuits, we've got an inductive time constant. L over R. So it's a little bit different form for us to remember. So, rising current sounds like it's going to increase, and we've got this 1 minus E stuff, so that's exactly what the plot would look like. And if you remember from RC circuits, based on that equation, what's your maximum value going to be, your Imax value going to be? E over R, yeah, that stuff out front, that gives us the max value. Good. That would be current I sub t as a function of time. So at time equals 0, right here, the inductor blocks current completely, and no current is going to flow through the circuit.
That's for sure no.
And then gradually over time, the inductor calms itself down and allows current to flow bit by bit. And as the current levels off, the induced EMF goes away because it's not changing as rapidly until eventually, as the current is constant, the induced EMF is 0. And at that point, it's like, we call that a short, where the inductor is like the inductor's not even there. Short. So it's like this is gone at time equals infinity, and you've just got a battery and a resistor. That's how the circuit looks. I'm using lowercase I to describe a changing current and capital I to describe a fixed constant current. That's sort of the shorthand or the symbol issue that's going on there. So this is exactly what we plotted, and then at one inductive time constant, if you plug that into the equation, you see that your current will be at 0.63 of its maximum value, so about 63% of its maximum value after one inductive time constant. So at any given point in time, you could also solve for the voltage drop across the inductor or the voltage drop across your resistor. So this shape shows you that the voltage drop across the inductor starts out high and decreases gradually over time with the max value of E, that's E of the battery. So this is essentially your induced EMF. E sub L. That's your induced EMF. It's going to start out high and go to 0. And then the voltage drop across the resistor, based on the form of this equation, shows that, of course, the current is 0 to start, so there's no voltage drop across the resistor to start. So that one rises while the voltage drop across the inductor falls. Any questions about the RL circuit during the rising current condition? Do you guys want to take a 5-minute break before we do falling current? Kind of.
Well, it's 20 minutes to 12.
It is, so
Just
we
till
can
lunch.
just power through if you want.
Sure.
You said small I was for the changing,
Yeah,
and
small
the
I
large I
is
is
for
for
a
current
changing
constant.
currents.
Yeah, okay.
Actually, I'll make these small i's.
Small I is what now? Changing current?
Changing current, and big I is if the current is
Constant.
reached a constant value, like at I max over here. Okay, so if you guys are free of questions, then we'll move on to the falling current case. Okay. So for falling current, the idea is we move the switch to position B, but you need a special kind of switch. You need a make before you break switch so that it will make contact with B before it disconnects from A. The reason is, if it disconnected from A, it would be like instantaneously turning off the current, which would be bad, because then your induced EMF is going to spike, your current is going to drop in as little time as it takes for current to stop flowing. It's going to create a huge B field from your inductor, and that could destroy your cell phone that's sitting on your charging pad, right? So we need to disconnect or connect to B before we disconnect to A. That allows the current to go away slowly as it dissipates through the resistor. So your resistor is the control valve to how quickly the current falls off. And so you'll need to make sure, if you're, say, doing your senior project and you create this little charging pad for your cell phone, you want to pick the correct resistance so that you never get a B field that's so big that it destroys your phone. So, so that's what we do. So we connect to B and then we disconnect from A. And then, once we're connected to B, this is the circuit. You just have the inductor and the resistor. So at time equals 0, you still have current flowing this direction in the loop. And now it's decreasing. It's going to go away, and as it goes away, it burns up through the resistor. So our loop rule equation looks like this. We solve the differential equation, and so the current, as it's across the inductor, has that form of e to the stuff. So that's just starting high and falling off. And then since I is decreasing, your induced EMF is down. So the current doesn't switch directions. Like with the RC circuit, when you switched to you move the switch in the RC circuit, the current switch directions. It doesn't switch directions for the RL circuit. All right, now, instead of putting I max here, I put I initial because you might have decided to move the switch before this got back up to its maximum value. And so wherever you stopped it while it was in the rising current state will be your I naught when you move it to your falling current state. If you waited, they say a very, very long time, that's their way of saying you wait till it's a steady state current, and then you switch it, then I naught will be equal to I max. So again, this graph is going to look something like this, with your initial value being I naught. And then we've got our similar equations for the induced EMF, or V sub L, across the inductor, and your induced voltage, or not induced voltage, but the voltage across your resistor. And both of those have just E terms, so they're both decaying, because of course the current's going away, so you gotta get everything ending up at 0 when you're done. And just like we saw with the RC circuits, most of the time when we're looking at these problems, we're always looking at the extremes. So we're looking at time equals 0 and time equals infinity. And that's not necessarily having to do much with the equation other than just logicking whether it's going to be its maximum value or whether it's going to be 0. Oh, there's a minus sign here, excuse me. Let me include that. I am gonna double check this equation because the units don't look like they would work out right. It's like remembering somewhere in the depths of my brain that was not correct last term. It's not, so VR is I times R. Oh, VL is L di dt minus L di dt. So L, and then our I equation, d dt of I naught e to the minus t over tau sub L. Oh, which